All good right now also? It's a bit too, isn't it too loud? Is it okay? Okay. I hear an echo. Let's see. How about now? Better? Okay, the echo is gone at least. I don't know if it's better, but let's see. Okay. Hopefully everyone is here for the seminar course, Computer Architecture. That's good. This is our first meeting. I'm going to give you an introduction on logistics and also set the mindset a little bit to begin with. If you're in the computer, how many people were in the computer architecture course just now? Oh, okay, you can sleep for a while until we get into the logistics part of it. We're going to cover some overlapping content. That's why I say that. But how many people took DDCA last semester? Is it last semester? Okay, how many people took it spring 2023? Okay, so you guys, I see some familiar faces, fine, that's good. Yeah, so you didn't have enough of us that you had to come, huh? Hopefully it's interesting, yeah. So we will delve more into, if you're taking DDCA, we'll delve more into computer architecture in a different way. We'll really discuss some interesting papers that you're going to present, and we're going to talk about them. Hopefully it'll be exciting. We haven't constructed the paper list yet, but we're going to work on it soon and release it. How many people are taking the course? Just to, because some people are TAs, so it's hard to decide. So you're all registered for the course, okay. There are actually more registrants than people who are here, so I wonder if there's anyone online. Is there anyone online? Nisa? Konstantina? Zoom? Well, maybe they're watching on YouTube, then we don't know if they're online. Okay, anyway. Okay, let's start. So if you have not, I mean, I've already introduced myself, but last semester I was on sabbatical at Stanford. So you guys took it before last semester, before DDCA. So now I'm back and we're teaching courses. Just to give a quick introduction, I've been here for about 8 years. Before that, I was a professor at Carnegie Mellon University, where we did research on all of these topics and some others as well. Before that, I started the computer architecture research group at Microsoft Research, and we did a lot of exciting things. We may cover some papers, who knows, related to that. Maybe not exactly the same papers. I spent a lot of time in industry over my career, and that's actually a nice thing to discuss things with industry, both informally and officially. So in my previous sabbatical, I was at Google and VMware, and I spent a lot of time at Intel and AMD in the past. Before that, I was kind of in your shoes. I did my PhD. How many people are doing PhDs here? Other than the TAs. There you go. There's someone who's raising his hand because he's going to finish his PhD very soon. Hopefully. Yeah. He's Geraldo. He's one of my senior PhD students. Okay, yeah, I did my PhD in computer architecture at the University of Texas at Austin. And before that, I was a bachelor's student at computer engineering and psychology at the University of Michigan. Let's not go before that. We could, but it'll take a while. So you can reach me over email, or you can find out more about a lot of things that we do on my website, or at least linked from my website. But clearly here for computer architecture, we work on all of these topics, and hopefully we're going to actually cover some papers related to all of these topics. Memory and storage systems, robust hardware, which encompasses security, safety, predictability, reliability, availability, hardware software cooperation, new computing paradigms, and architectures for special and important applications like bioinformatics, machine learning, medicine. Hopefully there will be a good spread of papers. It depends on what you choose also, because we're going to give you a selection of papers that we think could be interesting to study. And we also try to minimize overlap with past semesters. We don't want to keep studying the same paper over and over. It gets boring for the TAs at some point, you know, and me also. I mean, it never gets boring. There's always something else to discover, but we try to diversify in that sense. So there'll be a selection of papers, and then you will choose some of those papers. We're going to talk about that process later on. Does that sound good? Okay. This is my research group. You will see some of these faces. So this is an older picture, actually, but you will still see some of these faces. I see Geraldo over here. Look, the young Geraldo without a hat. Yeah. Yeah. And you can learn more about these folks and the research we do in our newsletters. We've been releasing these newsletters somewhat regularly, as you can see. And the most recent version is relatively recent, actually, July 2024. And can you learn more about the research topics, etc. At some point, if you're interested in doing research in computer architecture, it's good to know what else is going on. Clearly, we're not going to cover everything in this course, right? We're going to cover only at most 25 papers, depending on how many of you choose to remain in the course. Hopefully, you will all choose because it's exciting, I think, but it's your choice. Okay, so if you want to learn more about the group, we have a lot of material. So you can find that online. And these are folks who have graduated. There are more people who are going to graduate. I think they're kind of in the back, some of those over there. You can learn more about their research also by clicking those links. I have a lot of thoughts about computing futures, etc. We'll share some of those during the discussions over here, but you can find more about that. And if you ever are interested in doing research following a PhD, for example, or further education, you can learn more about my perspective on these things online. How many people are interested in doing research? Well, okay, more than, well, come on, TA should not lift their hands. They're polluting my data set. I should have a nice data set where, can you raise your hands again? Okay, that's a lot of people, that's good, yeah. Some polluters are still there, yeah. Okay, cool. Yeah, I mean, if you're interested in doing research on these topics, please feel free to talk to us. We do a lot of research on the topics that we're going to cover and also other topics that we may not cover, depending on the selection of papers. But before that, I will give you an overview of what we're doing, because you'll interact with a lot of the mentors who are essentially students of mine, who are going to guide you in the paper reviews. And this is going to be an important part of the process. In fact, I'm going to quote some people who have taken this course in the past, and they all like this interaction with the mentors over time, because that gives them an ability to iterate over their presentation and thought processes, etc. It's good to get feedback on your presentation so that you can improve over time. And it's an integral part of this course. Okay, but the research we do is really, in the end, to enable fundamentally better computers, better in all aspects. I like to think about it. We work in computer architecture, hardware, software interface, co-design, systems, bioinformatics, and security. And we touch on all aspects of the system. There's nothing that's like sacred ground in the sense that you cannot touch. Everything is touchable. Everything is changeable. And that's a good mindset in designing better systems going into the future. Because the thing that you think may not be changeable or may not be interesting may become a bottleneck, as we're seeing today a lot with memory. And we're going to talk a lot about memory in this course. And if you've taken DDCA, hopefully you understand the importance of memory as well. Even though DDCA, we talked a lot about computation, we switched to memory toward the end, right? Okay, these are some of the current research topics that we are following in the group, and some of the papers will be related to this. We're interested in designing fundamentally robust, secure, reliable, and safe architectures. Fundamentally energy efficient architectures, like memory-centric architectures, for example, reducing the energy and improving the sustainability, reducing latency and making things more predictable from an architectural perspective, and also fundamentally intelligent and evolving architectures that make better decisions over time. So as opposed to designing a system that's very rigid, that keeps making the same decision over the course of 10 years, 20 years or so while it's deployed, having a system that can improve itself over time, that can learn from the circumstances, workloads, users, etc., and that can over time adapt and do much better. I think this is a very important direction going into the future, because that's what really enables progress, I think. And also we're going to talk about architectures, and we do research on architectures for machine learning, AI, genomics, medicine, and health, and this is going to be a much bigger area into the future. I think all of these are important areas, clearly, but yeah. You've seen this picture if you've taken DDCA, and if you were paying attention, at least some little attention in the previous lecture in computer architecture. So how many people do not fall into those buckets? They have never taken DDCA nor attended the previous lecture, computer architecture. Okay, so there's 4 people. That's good, yeah. Maybe I'll ask another question. How many people are here from the computer science department? Okay. How many people are here from the ETET, or electrical and computer engineering department, I like to call it? even though the department calls it ETET. I like electrical and computer engineering, but okay, that's good. Yeah. Okay, we have a good balance. How many people are, again, don't fall into those buckets? Okay, there's one. Okay, that's good. Cool. Okay, so we're going to cover all of these different spreads, but how many people have not seen this picture? Maybe I should have asked that question more directly. Nobody has seen this picture. Fine. It's okay it's good to, don't be shy basically in this course, ask questions, be critical. Okay, so this is the picture that shows the transformation hierarchy today. Basically, in computing, we solve problems, and ideally, we solve problems by orchestrating electrons in modern technologies, but unfortunately, we don't know how to speak to electrons directly, right? I cannot speak the electron language yet, and humans have not figured out how to speak the electron language yet. So they build interfaces to cover up for the fact that they cannot speak the electron language, right? We translate the problem into an algorithm, which gets written in a language, it executes on a system software, and then it gets translated into a language that the machine could interpret that is implemented using a particular implementation called microarchitecture that's implemented using logic gates, which is implemented using devices which operate based on the electron physics principles, right? That's the hierarchy. And computer architecture traditionally has a narrow view of the hardware-software interface and the microarchitecture. That's the traditional architecture. But in this course, and more recently in the computer architecture domain, people have been taking a much more broader approach because of a lot of constraints that we've been facing in system building, complexity, and also technology scaling, which is across the stack, basically optimizing algorithms and devices across the stack. Still, our core is over here, but we're going to touch upon a lot of topics that do this sort of optimization. And I'm going to motivate this a little bit in this lecture before I go into the course logistics. So the reason this is happening today is because we want to maximize efficiency, performance, robustness. And if you just try to improve the interface and the microarchitecture without improving the algorithms together with it, then you have limited options essentially. It's much better to actually take an expanded view and co-design a system across the stack, basically optimize the algorithms such that they fit the devices and vice versa, and also design the interface such that it's much more efficient for the particular workload that you're executing. For example, a machine learning workload, or a genomics workload, or a database workload. And if you do this, this leads to much more higher efficiency, performance, and also robustness. And we will see some papers, I think, hopefully we will cover some papers that demonstrate this in a novel way. At the time they were written, they were novel, hopefully. One of the things we're going to question when we read the papers is this novel, right? Of course, you should always evaluate a paper for the time they were written at. If they were published in the 1960s, it's more likely that they're going to be novel. If they were published in 2024, it's probably less likely, but there could be novelty there. And one of the tasks in this course when you evaluate papers is to understand, figure out how to do that. And that's a very good skill to have. And it's not just novelty. We're going to focus on other things in a paper, like the question the idea, what are the trade-offs? Do some critical thinking. And that's what I would like you to take out of this course in the end, critical thinking. Hopefully across the stack as much as possible. Okay, I'm going to give you some principles that we use also in this course to set the mindset, but teaching and research are things that I enjoy doing. And I think these are the same thing with one key difference. In research, you educate other people on things that no one knew about. You figure out something novel, and then you educate people with that. In teaching, you educate people about things that everyone knows about, or everyone could know about, right? So it's a known thing versus unknown, or previously unknown thing. So in that sense, research and teaching are really important. I could go into more philosophy over here, and if you've taken the previous course, you've got that philosophy, but we're going to move. So we have a lot of other courses also. Some of you have taken the digital design and computer architecture course. In fact, the spring 2023 version. That's good. Hopefully you enjoyed it. We have another advanced computer architecture course. If you want to learn more about computer architecture, you can take that. You don't have to take it right at the same time concurrently, but there's no problem taking it concurrently. There will be some overlap in the content of the courses, clearly, especially the first lecture, and maybe some initial lectures as well. But this is going to be a very different course, clearly, where you will present the papers. So focus is really on presentation, analysis, discussion, brainstorming, etc. It's a seminar course in the end. Whereas the computer architecture course is really a full course where you do assignments, where you essentially look at different parts of the system. And also we cover a lot of fundamentals and cutting edge research. Okay, there are other courses also. I'm going to go through this relatively quickly. If you ever want to brush up your like background on a particular paper or something, you can always refer to the digital design and computer architecture course. I think you will find it useful if you've taken it. If you haven't taken it, don't worry. This course doesn't require that much background, but you always can refer to it. And you can, of course, always refer to other stuff. There's everything online, right? Nobody is limiting you from referring to anything online. Just make sure that you, like if you use something from some other work, make sure you reference it, right? That's really important. Okay. Okay, there are other courses that I'm going to skip over here, just to give you an idea of the breadth of courses that we have. We also have some more specialized courses on DRAM and RowHammer, emerging memory systems. These are normally bachelor's courses in the ETED department for PNS. These are called PNS courses, but you're welcome to examine them online as well. These may change over time, right? We also have a processing in memory course. There will be some processing in memory papers, I'm hoping. You will choose some of them. And we have a genomics course. There may be some papers on that. Heterogeneous systems course. This is actually focused on GPUs and heterogeneous programming, and hardware software co-design course. And an SSD course. We'll probably have papers selected depending on your selections during this course. Okay, you can find more information about the courses over here. We do a lot of both online and offline activity on special research sessions, like we've been organizing special sessions on in-memory processing, which is a hot topic right now. When we first started working on it, it was not that hot, let's say. Now it became very hot, which is good, because this is, I think, how things should evolve. People should design more memory-centric computers, and we will discuss that also, advantages and disadvantages, if we actually get to study a paper related to that. We've also been organizing PIM tutorials, processing in memory tutorials, and various conferences. And these are all online materials. You can, if you're interested in computer architecture, you can find all of this information online. And these are actually kind of the function of these slides are actually pointers to those online materials. And one of them is going to be organized in Austin in November, and Geraldo with his hat is going to organize it. Are you going to deliver the tutorial with the hat? I see. Okay, so you're hiding something over there. I see. Okay. Okay, you can find more. So we do a lot of open sourcing of artifacts. If you ever want to get your hands dirty, this is a good way. Trying different artifacts. These artifacts are actually used heavily by academia and industry. For example, Ramulator, RowHammer, etc. You can find a lot of information online. And we try to open source as much as possible. This is one of the philosophies that we have. Okay, I'll go through some basic principles to set the mindset that will be helpful in thinking about this course. I've already talked about this one. I think one thing that we focus a lot, clearly being a research group, is to focus on insight. Basically, we want new ideas, we want new insight. And one of the functions when you read papers is really to understand what kind of new insight and what kind of new ideas a paper brings to the table, brings to the state of the art. And also, not just that, but also what kind of new ideas do I have inspired by the knowledge that I gained after reading this paper. This is actually a very good way of making progress. Later, I'll show you a virtuous cycle of scientific progress. If you actually critically analyze the paper, understand what it's doing, and develop ideas based on that, you actually get a lot out of the paper, right? Who knows, maybe you'll come up with a PhD thesis out of this, right? That's actually interesting. We focus a lot on learning and scholarship. I guess what else could you focus on? I guess you could focus on money. we don't care about money here in this setting, but you could care about money. You could be an entrepreneur, and hopefully you'll get something out of this also, because presenting your ideas in a way that is actually very clear and is really important. In the end, well, I guess you can make money without being extremely technical also, but anyway, we're not going to talk about that. But if you want to actually do a technical startup presentation of your ideas are extremely important. So hopefully this course will help you with that aspect, especially with a critical crowd. You may have a critical crowd asking you questions, right? Okay, so we value an environment that values free exploration, openness, collaboration, hard work, and creativity. These are things that we do in our group. And I think this course exercises a lot of these aspects, I should say. Basically, this is free over here. You can ask any question related to a paper. It's open. You can collaborate on studying the papers. In the end, you need to present your own paper. one person, but you can certainly get help from others to discuss. If that improves your presentation, why not, right? That's perfectly fine. And I'm very interested in creative ideas in general because that's really necessary for progress, right? We should always question what has been done in the past to improve the future. And the real big ideas come out of creativity, I think. Okay, I strongly believe that the quality of your work defines your impact, and we try to focus on quality, and we evaluate the quality of the papers in this course, basically. So some of the things that we will evaluate will be the technical quality, scholarly quality, etc. So these are good things to keep in mind when you're evaluating papers. I'm going to talk more about that. So my suggestion to you in general, I think, is follow your passion, whatever you're doing. Hopefully you pick a paper that you're really excited about here. But don't get derailed by naysayers also, because you will always have people who will criticize an idea, even though the idea may be good, right? So I think going back to over here, you may do very good quality of work, but they may not be appreciated right away. And we're going to see maybe some papers over here that have gone through that, but it may be appreciated later on over time, especially if it's solving a real problem in a real domain that really is important, right? So don't get derailed. Of course, take feedback in a nice way, but never get derailed if you're trying to do something big. Because all of the currents are against doing something big in general, right? If you think about that. If you get derailed quickly, then you will never do something big. Okay, but you need to work hard to do that, right? Building infrastructure is important to show the benefits of the ideas or the trade-offs of the ideas. Working hard is important. And I think being resilient and focused is really important. In the end, you have some goal. For example, we'll talk a lot about processing in memory. Making it happen is really important, I think, in the end. And there are a lot of things that may need to go into making it happen. It may not happen overnight. It may not happen over many decades. It may not ever happen. But that doesn't mean that you cannot be resilient and focused to enable something like that, right? Enable a different paradigm. Okay, I think I already said this one, which kind of ties into the previous one and this one. So I think in the end, if you follow some good principles and have the right mindset, have the right focus, I think the sharp focus maybe to make it happen, you can really make a good impact on the world. Okay, I have a lot of this philosophy online also, so you can learn more, but feel free to ask me questions at some point. So this is one of the required readings, although we're not going to evaluate you on it. Is it required? Like, are we going to have an evaluation in that sense? No. Okay, it's required in quotes reading. I would definitely recommend you read this paper. It's Richard Hamming. I think you know about Richard Hamming, right? If you took DDCA, I referred to him multiple times. If you didn't take DDCA, in the previous lecture, you've seen it. But basically, Richard Hamming was, how many people don't know about Richard Hamming? I'll ask that question. Always asking the important question is important. Okay, that's fine. Richard Hamming is a computer science researcher who essentially invented Hamming codes. And he actually was really I should say probably the first discoverer of control coding theory, error coding, essentially, error correction codes, among other things. And he was at Bell Labs over his career. And because of his contributions, he won the Turing Award, essentially, which is the kind of like the Nobel Prize in computing. Sometimes these prizes are overrated, but Richard Hamming won it in a very deserved way. Not all awards won are deserved. But I think in case of Richard Hamming, it's a deserved award. Keep that in mind also. It's good to be a critical thinker, right? If you're a critical thinker, you have a good mindset and you set what's right and what's wrong based on like real things, let's say. Okay, in the end, basically Richard Hamming delivered this talk at Bell Labs where he spent most of his career at the end of his, during different parts of his career. And he basically talks about a lot of philosophy of research, etc. So if you want to become a researcher, I would definitely recommend reading this. And I agree with a lot of these things that he suggests. And this is him in later years of his life with his cat, with an unknown age. Okay, but basically, I'll go through some of this quickly. If you really want to be a first-class scientist, you need to know yourself, your weaknesses, your strengths. It's like critical analysis that we're going to do in this course for papers. So you just apply it to yourself. I think a lot of the principles that we apply in this course to papers apply to everything else that is done, not necessarily technical things, everything essentially, and your bad faults, etc. And basically, he says, question things and improve things. That's how I would summarize this paragraph. How can you convert a fault to an asset? And He basically says the successful scientist changed the viewpoint and turned what was a defect, maybe from others' perspective, to be an asset. So maybe I'll pick an example, right? This is not a good example, but for example, a lot of people know about RowHammer here. How many people do not know about RowHammer? It's okay, don't be shy. Really, everybody knows about RowHammer? Okay, even if you have not taken my courses, I'm not going to be offended. Okay, well, RowHammer is becoming interesting then. Okay, you will learn more about RowHammer. So, but this is the fact that you can introduce bit flips by hammering a row, right? This is a defect, right? In DRAM chips, this is a defect because you cause bit flips. But some people have used this as a way to identify the device as a physical unclonable function. So now it's an asset, right? So you can think about it in different ways. This is not a good example because I wouldn't use it as a puff. In fact, people have later shown that using RowHammer as a puff is not a good way of building puffs. But these are papers that are written. So anyway, basically, he goes on and says that I claim that some of the reasons why so many people who have greatness within their grasp don't succeed are they don't work on important problems. I think this is important. Like if you're really tweaking some non-important thing, maybe you're wasting your talent, right? I always say this sometimes when I see people working on smaller ideas. It's better to actually work on bigger ideas, maybe harder and maybe more risky, but that will enable you to become do something much bigger, right? They don't become emotionally involved, maybe focused and resilient, right? They can give up easily. Whereas if you're I think what he means here by emotionally involved is that you really say, okay, I believe in this idea. I'm going to make it work. Of course, I'm going to take the scientific approach to understand what is possible. But if you're an engineer, you also have a lot of levers in your hand to enable an idea, right? We're not just explaining the world. We're just also changing the world by building systems. So they say, I believe in this idea. And if you're not emotionally involved in the sense that if you really don't believe in that thing, someone says, oh, I reject your idea. After 5 rejections, you say, oh, okay, I'm done. I don't believe in this idea anymore. Basically, you lose greatness that way, I would say. And I agree with Richard Tamming very much over here. Okay, I will pick on this one also. They keep saying that it's a matter of luck. Basically, people who have graspness or potential greatness saying that I need some luck. But it's not really luck. Hopefully my storage system will work well right now. But Louis Pasteur, for example, said that chance favors the prepared mind. This is actually a slide from DDCA, if you've taken DDCA. And I had this quote underneath. So really you can bias the coin to yourself. If you're prepared enough to understand a domain and the problems and have enough preparation to have potential solutions to those problems, you may have an opportunity to actually really enable those solutions, and you can enable it. If you're not prepared, you may get the opportunity, but you may not even see the opportunity, right? Because you don't know enough about the domain, you don't have enough preparation. So preparation is always something that favors the luck on your side, if you will. You can be lucky, but if you don't have preparation, that luck is useless, right? It's very hard to get that luck. Okay, so you can read more about this. I took a lot of time on this one, but I like this paper. Well, it's not a paper, it's really a transcript of a talk, but I would definitely recommend it. There's a video also of it. Any questions? Okay, now let's jump into the role of this course a little bit. So we're going to talk about computer architecture. I've used the slide in DDCA and the previous lecture. So if you remember it, that's great. But computer architecture is a science and art of designing computing platforms. This is the broader definition: hardware, interface, system software, and the programming model to achieve a set of design goals. And we always try to achieve a set of design goals. This could be, I'm going to go through this basically. This could be highest performance on Earth on workloads XYZ. This is like a supercomputer, right? And today people are building a lot of machine learning supercomputers to accelerate machine learning. It used to be some other workloads, more scientific workloads, supercomputers. But this is a very restricted domain, and you want to get the highest performance in it. Or it could be a mobile computer or a smartphone where you want to get the longest battery life at a form factor that fits in your pocket at some cost budget. Or it could be a more general purpose computer. You want to get the best average performance across all known workloads, maybe thousands of workloads, at the best performance cost ratio. These are clearly different types of systems. But in the end, a lot of fundamental principles are similar. If you understand the trade-offs you're making in the design, if you understand the trade-off you're making when you actually change some component or implement some component in some way, you can actually design any component, in my opinion. As an architect, it's good to feel that way. So it's not that hard once you have the principles. Okay, but this requires a lot of critical thinking also, right? You have to really understand different aspects of a problem and the trade-off space really well. Because in the end, there are a lot of metrics that we also care about. It's not just performance, it's not just energy, it's not just the costs that are actually here. It's also robustness, it's also security, it's also safety, for example. It's also complexity. Yeah, there are many other things. Okay, I have that slide somewhere else later on. Okay, just to jog your creative juices, these are some pictures of computer architectures. These people are doing DNA sequencing in space, I think. And there's more we're going to do in space going into the future. This is your favorite Mr. Bean from DDCA, probably. I still like it. This may be more reliable than the self-driving cars that are out there today. Another self-driving car. And clearly people are designing chips for these workloads so that they can optimize across the stack. So my point earlier on we want to optimize across the stack is really happening in industry. Car companies are really designing their own chips so that they can actually do machine learning, inference, and training, and also do the self-driving in a way that where they can optimize their software on the hardware that they themselves design. This is a data center. This is a supercomputer, more supercomputers, and there are a lot of these, clearly. Clearly, we're looking at not just chips over here, but also systems, entire systems, right? And this is actually interesting because computer architecture, even though the traditional definition is in the middle, hardware, software interface, and microarchitecture, which is really the chip, it's really important to think about the broader definition, right? Because you have many chips and you need to connect those chips in a way. So it's really system architecture, and that's what we do. And we're going to see some papers related to that, I hope. Okay, this is a more recent specialized machine learning accelerator that you may have seen in DDCA. If you took DDCA, we covered systolic arrays. How many people know about systolic arrays? How many people don't know about systolic arrays? It's okay. Again, we may cover systolic arrays. It's basically a specialized acceleration mechanism to enable computation on the data you bring without writing the data back and forth too much to memory. The data flows, or the input data elements flow into a matrix, for example, and you do matrix multiplication, that matrix, while reusing the data that's generated by the intermediate units. This idea, systolic array, was first proposed in 1970s by H.T. Kung, who was a professor at CMU at the time, and he did a lot of work on that topic, and it never took off commercially until, well, this is not the first version, but until Google actually built systolic arrays to accelerate machine learning inference and training in their data centers. And the reason they did use a specialized accelerator like this is because they wanted to, well, there are multiple reasons, but they knew that their workload really well, machine learning, inference, and training, and they wanted to accelerate it in a manner that's very efficient, high performance, and also less costly to them. So they wanted a system where total cost of ownership is lower for them. If they actually source the products from somewhere else, let's say they use GPUs for this purpose, it would be more costly. I think people are seeing that more and more right now, because clearly some company that's creating GPUs is charging people a lot for those GPUs. But that would be more costly. Not only more costly, but also they could not customize that chip to the workload that they really know very well. This is a software company. They should know their workload really well if they know what they're doing, right? So they could customize across the stack, right? But never underestimate the cost argument also. Do I build my own chip? It's a lot of investment, but that investment may pay off. Okay, this is a GPU, which is clearly being used a lot in machine learning, inference, and training today. And this is kind of the evolution of recent GPUs. GPUs were not always machine learning, let's say, machines, right? They used to be graphics processors. They used to be in almost every processor to accelerate graphics. And at some point in late 1990s, early 2000s, people started saying, oh, I have this graphics processor in my computer. Can I do something else with it? Can I accelerate my other workload that has nothing to do with graphics. And they figured out how to painfully program this thing, and they showed benefits. And over time, a company like NVIDIA figured out how to actually make this more programmable to the outside world in a manner that's actually very useful to many workloads. Like we've covered some of this clearly in DDCA. If you don't know about GPUs, you can refer to DDCA. And over time, it turned out this model was actually very nice for machine learning, but it was not enough for machine learning. So over time, this company also started adding things similar to this over here, which are tensor cores, matrix multiplication units, right, inside the GPU. So if you look at a GPU today, it's a general purpose parallel machine that uses single instruction, multiple thread programming model, but it also has acceleration capability, specialized acceleration capability today. So it's general purpose and special purpose at the same time. So you can have heterogeneity in the system. But also don't underestimate the interconnect. So these latest GPUs have a small amount of memory. They figured out that you needed high bandwidth memory to access large amounts of training data or inference data. But this high bandwidth memory cannot be built with very large capacity because it's 3D stacked, etc. And there are a lot of issues which we may discuss also. So you need to connect multiple GPUs together. And in order to connect multiple GPUs together, you need to have some very good links. And these are some links that are designed at NVIDIA. These are NVLink over here. You can see these are eye diagrams that show the quality of the signal that is being communicated, which is really interesting also, but we're not going to talk about that. But you can see that the bandwidth between these GPUs is quite high. So this is one of the examples where computer architecture is not just about the chip, right? It's really about the system. It's about computation. It's about communication. It's about memory, which is kind of not shown here. It's kind of hidden inside the GPUs. And it's also about storage, which is not here. Okay. So one of the reasons why people are also optimizing across the stack, and this is happening across many systems companies, is really these models have been growing a lot. And as a result, they're pressuring the system a lot more, both in terms of computation as well as memory, both memory capacity as well as memory bandwidth requirements. In fact, latency requirements also. So you can see that interconnect topology is important. These are some example interconnect topologies from NVIDIA, and that has been improving over time. So basically, you cannot fit these models in a single GPU. It's very hard to fit them even in a single, well, definitely not in a single HBM memory, right? It's increasing, but it's not there. So you need to connect multiple GPUs together. And you can see that the interconnect topology is important. Hopefully, we'll read some papers on interconnects today, because I think it's going to be increasingly important. Okay, just to show you, these are some of the interconnects that we cover in the computer architecture course, actually. You can see that there's an all-to-all connection between these 36 units of GPUs here and these other 36 units. And there's some concentration employed within the 36 over here, such that 4 of them communicate through a single output link over here. Okay. Feel free to ask questions. I just want to give you an overview. But clearly, systems are becoming more complex, and also they're really hardware software co-designs. This is another totally different approach to building systems. This is a wafer scale chip. The chip is really literally this big. Normally, what you do is you take a wafer, you pattern the chips on it, and you essentially cut the wafer into different chips. But these folks said that, no, we cannot do that because our workloads are very intensive. We need a lot of compute, a lot of memory bandwidth at the same time. So we're going to not cut the wafer, and we're going to design a distributed system on this wafer, if you will. And this is, I guess, it's not the largest anymore. But as you can see, the comparison to the largest GPU is pretty staggering. This has 2.6 trillion transistors. I guess the new version actually has 4 trillion transistors because of Moore's law. Moore's law is still alive. Whether it's well or not is a different question. It's alive, but it's a bit sick, let's say. It's having difficulties in justifying its cost. So the cost of a transistor is not reducing as much as it used to. But people are still packing more transistors on a single, on a given millimeter square. And still there's some cost reduction, but not huge. Okay, anyway, but basically you can see that they can have 44 gigabytes of one-chip SRAM coupled with processors. These are SIMD processors, single instruction multiple data processors in this. So it's a lot of memory, but it's not enough memory. It's actually smaller than an HBM stack today. So what happens is if your workload is larger than this, what do you need to do? You need to connect them again, right? Connect them to connect multiple of these. Or you have another memory hierarchy. So in this course, we're going to question a lot of these. Maybe we'll cover some of these topics also. Like in past incarnations of this course, we covered systolic arrays, and there were good discussions. We may cover some more of those. And there are other things happening that are interesting today, where people are finally looking into processing capability on the memory side. So this is a startup in Grenoble, France, where they put a general purpose MIMD, fine-grained multi-threaded processor. If you've taken DDCA, you would know fine-grained multi-threading, which is what GPUs employ today, right, to keep their cores full. Processor next to each DRAM bank. So now you can actually buy this, you can actually program this. We may read papers related to this also. But it's not just startups, it's also some major companies that are looking into putting computation capability inside DRAM chips, main memory chips. These folks at Samsung and later Hynix, they've actually put specialized units that can accelerate matrix computations. Essentially, they're targeting machine learning again, which is interesting. And companies that have nothing to do with, well, not nothing to do with, but the companies that don't normally manufacture memory, they also are building their DRAM chips, as you can see, so that they can actually do better machine learning inference for recommendation. And more recently, people have been proposing interconnects that are more flexible. So when you go off chip, if your interconnect is flexible, it can enable abstraction such that you can offload computation, for example, to some other component in the system, some other device. It could be storage, it could be memory. And these CXL or Compute Express Link based interconnects enable that. Industry has been trying to move to that. We'll see if it really happens, but I think this is a good direction. We need more flexible interfaces such that we can do computation in other parts of the system than just the CPU, GPU, FPGA. And here, people have shown that you can offload computation to the memory side and the storage side. So the processing in memory landscape is very nice today, and we may see some papers related to this. Okay, so why are you in this course? Hopefully you're interested in doing all of these, as opposed to just getting credits. Who is interested in this course just to get credits? Don't be shy. I'm not gonna. Okay, nobody answers. Maybe because they're shy, but I hope that's it's not because you're shy. I hope it's because you want to learn things, and maybe you want to do things at some point. Even if you don't do things like this at some point, I believe what you learn in this course would be useful, like honing your presentation skills, figuring out how to present, answer questions, figuring out how to do critical analysis of your paper as well as others' papers. I think these are really good skills to have even beyond scientific and engineering fields. I'm going to mention that also. But basically, this is why we do computer architecture. We want to enable better systems, enable new application systems, enable better solutions to problems. And also, even if you're not enabling something new or new solution, even if you understand why computers work the way they do, you can still accomplish things. You can propose solutions, right? But I'm not going to go into the details of it. So today is a very exciting time to study computer architecture because of all things I showed you, there's no single architecture today that is dominant. You could argue that GPUs are dominant, but I would disagree with that. Yes, they're dominant in one particular workload, potentially. That may change if that workload changes significantly over time, which I hope it changes because the current exponential growth of that workload is not sustainable, in my opinion. It's really causing a lot of damage to our climate, universe, etc. That should change. But there are many, many different types of things that people are exploring right now because of many different issues. Again, I don't want to go through all of these because I do want to get into the logistics part of the course also. But I'm happy to talk about this, and you'll see some of these topics that we will touch on while we cover different papers. Okay, so what do we want to do? Basically, we will cover fundamental and cutting-edge research of research papers in computer architecture. We're going to limit ourselves to mostly research papers. They may be old papers, they may be new papers. A lot of them are going to be biased toward the more cutting edge because it's good to know the cutting edge. That's really important. And we have multiple components in the course that are aimed at improving your and hopefully everyone who attends, including mine, technical skills in computer architecture. I think that's really important. Critical thinking and analysis. It's always good to have that critical mind, as we mentioned earlier. and do an analysis in a rigorous way. And technical presentation of concepts and papers. So you will be on the spot kind of here, presenting things technically and wielding questions that may come up. Don't be shy to ask questions, please. It's always good to ask questions. The goal is really to have a discussion, and also see where we can take a paper, right? In both spoken and written form. So there is a written component of this course also that you will fill at the end, which is the synthesis report, which will hopefully synthesize a lot of things you have seen in the course. I think it's really important, as opposed to just giving your presentation and then getting feedback and then you're done with it. It's important to synthesize what you've seen. That enables much bigger thing than just presenting and getting feedback, I think. And also, hopefully, it'll familiarize you with major research directions in computer architecture. So my key goal is really to enable you to learn how to rigorously analyze, present, discuss papers and ideas in computer architecture. I think you got some of this in DDCA. If you've taken DDCA, you will definitely get some of this in the computer architecture course. But this course is really focused on presentation and discussion. So you will really go deep in a single paper. You may be sick of the paper that you're analyzing, for example. So hopefully you'll select a paper that's going to be interesting. That's why you need to focus on what excites you, right? Otherwise you read something that's really dry and terrible and you throw it away. That's also a learning experience, by the way. It's fine. You'll learn from those things also. But it may not be the most optimal experience in the end, right? In the end, but you have to do that. In research, you have to read crappy stuff and also good stuff. And what really is interesting is the good stuff, of course, right? You don't come up. For example, I don't wake up every day saying, "Oh, I'm going to read crappy stuff." It's much better to read good stuff. Okay. So we have some steps to achieve the key goal. At some point, I'll take a break, but let me cover this one. So we have steps for the presenter and steps for the participants. And you will switch roles, clearly. Most of the time, you will be the participants because there will be one person presenting. But at one instance, hopefully no more than one instance, you will be the presenter. At exactly one instance, let's say. So you will need to, I think, follow some hopefully good steps. Well, these are not really steps, but this is more like suggestions, right? Clearly, you need to read the paper. Hopefully, read it in detail. You'll need to absorb it. You may need to read more other related works or get your background to a level where you can understand the paper. You'll need to critically analyze it, think, and synthesize based on what you've seen so far, right? And prepare a clear and rigorous talk, and then present. And then you answer questions during and after the presentation, and maybe online as well. And then you analyze and synthesize in meetings after and at the course, at the end of the course, basically. This is more a synthesis report, for example. So there's a lot to do, but hopefully you'll learn a lot during the process. And meeting with the mentors is a really important part of this process, because I think a lot of these happen during that loop when you meet with the mentors. As participants, you still have some responsibility. You can come and sleep, of course, but that's one option. But hopefully it'll be more than that. Discuss, ask questions, and also think critically about what is being presented, right? You can also analyze and synthesize based on what you've seen so far. Like not only in this course, but in also potentially other courses, other things you've read, etc., other things you've learned. So hopefully it'll be exciting to everyone involved. So we'll have a lot of topics. This is not limited to all of these topics, but these are some topics that we've covered in the past in no particular order. I think all of these are important topics. Hopefully we'll have a good selection also. So if you have 22 papers, for example, that we cover, that's a lot of papers that you will get exposed to during the semester, right? If it's 25, it's okay. If it's 18, it's okay also. So it depends on how many of you end up here. Okay, so essentially, my goal is to enable you to think critically. That's probably the most important one. I think actually I've used the same slide for DDCA, if you remember. Think broadly, so we'll cover a lot of topics. Learn how to understand, analyze, and present papers and ideas. And get familiar with key steps in research, first key step. So if you read a paper, this is actually a step that you take in potentially being a researcher. And get familiar with key research directions, I think. Not just particular paper that you're analyzing, that's one direction probably, but there are many directions. You will hopefully see a lot of those directions. And we will also have some introductory lectures before we jump into papers. So we will give some area presentations on some topics. So that will also enable you to, again, see some presentations, ask critical questions, etc. So you'll have a chance to see some of these research directions in the first few lectures, maybe 3 or 4. I don't remember how much time we have for the schedule. 2, okay, wow. That's assuming everyone stays. I'm not discouraging you to drop. I'm encouraging you to stay. If you want to stay, we'll take everyone in the course. But if you want to drop early, not late. Because there's another person who probably is waiting in the wait list. We have a long wait list also that may want to take the course. If you drop too late, they will not have the opportunity to get into the course. Okay, so this is the virtuous cycle I promised. And I think that we're going to take a break right after this. But basically, a lot of scientific progress happens this way. Not everything happens this way. Sometimes you can come out of the box also, but you read critique papers or develop some background, understand the problems, and then you question and brainstorm. And then hopefully you develop new out-of-the-box ideas based on that critical thinking. And then hopefully you work hard to demonstrate your idea, maybe collaborate when needed, and then do great research, find something good, publish and educate others through presentations, and then keep doing this. This is not a bad approach, let's say. But of course, you may enter this from different places as well, right? Sometimes you may actually come up with go into a collaboration and start learning about new things, right? Or sometimes you just question and brainstorm without reading anything, and then that may lead to something new. That's tougher, of course. If you read more, then you can you're more prepared, right? Going back to this chance favors a prepared mind thing. But collaboration may get you somewhere easier. That's why having being in a research group that does a lot of different things and getting into a collaboration enables you to do something big more easily in that sense. Okay, I'm going to stop here and take a break, unless there's a burning question in the previous parts. No burning question. So let's be back at 17:20, 23. And then we will cover the course logistics, and then we'll be done for today. Yeah, hopefully it's not in the other room. I didn't do it. Okay. Nope. My voice is not doing well. Everything good? Shall we start? Okay. Okay, I don't intend to keep you for long. Whenever I say that, bad things happen. So let's talk a little bit about course info and logistics. I hope I will survive by the end of this lecture. I've already mentioned all of these, but there are two other lecturers. Mohammed is standing in the back, and Lenny is sick. Hopefully getting better. Hopefully I'm not getting sick. She's online maybe. Is she online?
Yes.
Okay. Okay, great. And they are senior researchers and lecturers in my group, and they've been involved in this course for a while. So feel free to ask them any questions. And we have a bunch of teaching assistants and mentors. Essentially, these folks are senior researchers, PhD students, master students, and interns in my group. Can we have a show of hands of the mentors, TAs? So you can see a lot of them. I don't know if everyone is here, but quite a few are here, as you can see. Okay, so please get to know them and their research, as they will be your mentors. You can find them online. I don't know if the online page is up to date, but they will also be your mentors. Depending on which paper you select, we'll assign mentors to you, and you will have these meetings with the mentors. Okay, so requirements. I require attendance for all meetings. This is important for a small seminar course. I don't normally require attendance in my lectures, but in where people present, I think this is important. Do we make exceptions to this? No, we don't talk about that. If you have a real reason for an exception, please let us know. Like if you're competing in the mathematics Olympiad, for example, and you're going to win the gold medal, then it's important. I mean, that's one reason, right? There could be other reasons too. In person is much more preferred because online is not that great. And it's great that you guys are in person over here. So every one of you will present one paper, and you'll prepare the presentation with engagement from the mentors. So it'll be full presentation, discussion, and question. Total about 45, 50 minutes. Sometimes it gets longer. Hopefully not too long. At least your presentation should not be too long, but the discussion can potentially be longer. Non-presenters participate, as we've discussed, right? Ask questions, contribute thoughts and ideas. This is great. I mean, in the past, we've had very good discussions, which inspired a lot of people. And it's better if you read or skim the paper beforehand. It's always good to do that, right? That way, at least you know what's going to be talked about. But this is not a requirement by any means. Well, you should read the paper you're presenting, of course. Right? That's critical. So non-presenters also take an online short quiz after each session. What is an MCQ? Okay, multiple choice questions. I don't remember acronyms unless it's a very common acronym. So every acronym should be defined. So 3 multiple choice questions for each presentation. You have 1 full day to submit. That's good. These are not that hard, I think, if you know the paper. Or if you attend the presentation and paid some attention. You can also study the slides. Slides will be online. And also we have an online review system. Hopefully people will participate online and discuss papers. And everyone gets to write a synthesis report at the end of the semester, and the sample is online, so you can find it and download it. Hopefully it's nice. This is the course website. We'll post all materials, including the papers that we're going to suggest that you choose from, plus other useful information, for example, links to previous editions of this course, right? And if you look at the links to the previous editions, you can see slides, you can see how people have presented things. You can even see some videos, assuming people have consented for those videos to be on YouTube. So you can see some fellow students who presented in the past. I think we have some recommendations also, right? I don't remember. Maybe we'll find that. In the past, we used to recommend some videos. Yeah, I don't think they're on the slides, but we can do that maybe. Yeah, it'd be good to add that, I think. Okay, yeah, please check frequently for announcements and due dates. Moodle is also there. This is where paper discussion happens and also assignment submissions happens. Quizzes, for example. will be there after every seminar. Okay, this is something required that you should fill. This is due next week. It's very simple information about yourself, why you're taking the course, etc. And we want this to be submitted on time. It's okay if you slack one day. But our goal is to make sure we have everyone's information so that we can schedule you for a presentation. Of course, not just this, you should also submit the paper preferences. There's also a simple homework. Hopefully this will be very easy. You can find it online. It's a review and critical analysis of a very simple paper. It's only 2 pages. You can take a look and figure it out. It'll be fun. But this is due later, as you can see. And then paper review preferences. We need to get working on this and give you a due date for this, because this is going to be important for you to choose, and we'll schedule presentations. And if we don't get your preferences, we cannot figure out magically how to assign a paper to you, so you'll have to drop the course. I hope that doesn't happen, because that does eat a slot from someone else, as you can imagine. So please send your preferences. So since this report, this is usually due 1 month after the last lecture, so there's still a long time for this one. But these are essentially questions based on everything that you have seen, you have read, you've listened to, and you have experienced in the course during the entire semester. That's why it's called a synthesis report. You really synthesize the entire experience that you've had. And again, this is important to submit. Part of your grade will be determined that with this. I'm going to go through the grades later on, but before that, I want to talk about how to deliver a good talk. Is there anything unclear so far? Any questions? Okay. I don't see any hands, but if you have a hand up, please shout if I don't call you. Okay. So how to deliver a good talk. I think this is an important thing to learn about, and hopefully you'll exercise in this course. This is the anatomy of a good paper review or talk. It's important to specify in the first slide who has written the paper that you're going to analyze. Where did it appear? What is the title? This is really important. It's not good to omit this because these questions may come up, right? Because people are going to get into the paper, and should they really be thinking, oh, when did this paper was published? Right? Was it 1960s or when was it 1999? And that makes a difference, right? Even 99 is old these days, but when I was first starting my studies, it was not old. Okay, and then there's a summary, executive summary. What is the problem the paper? I'm going to show you some examples of this. What is the paper, the problem the paper is trying to solve? What are the key ideas? What are the key insights? What are the key mechanisms? What is a little bit about implementation, if that makes sense to add it into the summary? What are the key results and key conclusions? And then we're going to talk about strengths. And so summary actually can take multiple slides, as we will see in some of the example presentations. There will be some example presentations that we're going to post later on. So this will take some time. I'll show you some time breakdown or suggested time breakdown. There's no rigid rule, of course. So you can discuss a lot of these in detail, but it should start with probably an executive summary to begin with, very short executive summary. And then becomes a critical analysis. What are the strengths of the paper? The most important ones. Basically, this should be an ordered list. You can nitpick, no problem. Nitpicking is good, actually, for any kind of progress, but don't reorder things, meaning don't start with the nitpick. Start with the big items. What is the biggest strength of the paper? It opened a new area. It asked a question that no one asked, and this really opened a new field. That sounds like a great paper, right? In that case, maybe I don't care if there are a bunch of writing mistakes somewhere here and there, right? So you can overlook some lower order problems if the higher order is very big. Does that make sense? So it's always good to think about that ordering. Okay. Weaknesses, again, the same way. Start with the most important ones. Again, you can nitpick. Oh, okay, I was talking about strengths earlier, but maybe, so you probably, the strength, you should not start with, oh, this is a wonderfully written paper. It's an excellent paper in terms of writing. If that's the only strength in the paper, then the paper is a problem, right? Probably nobody wants to write that paper. I don't want to write that paper if that's the only strength in my paper, right? Hopefully there's a bigger strength, meaning, oh, it solves an important problem with a creative idea, right? That sounds much better, even though it may not have opened the new direction, which is probably a higher order strength. This is still pretty high up on the list compared to writing. Okay, weaknesses the same way, basically. start with the most important weaknesses. If there's a fatal flaw in the paper, meaning that they made an assumption, for example, that's really wrong and that really affects the key results, then that should be stated. Most papers don't have that sort of fatal flaw, hopefully. There are some that do have that fatal flaw, of course. It's good to identify it if there is, but we probably won't cover those papers, but there may be, who knows, right? Maybe you'll be the first one to identify a fatal flaw. That's also possible, unlikely. Okay, but this is where you should really think critically, because strengths, I think it's important for you to think critically to figure out what are the real strengths, because strengths may be written in the paper, but those may not be the real strengths of the paper, right? The paper is written with some perspective in mind, but the real strengths may be visible 20, 30 years down the road, right? Does that make sense? I'll pick on the systolic array paper, right? For example, it was written in the 1970s with some perspective in mind, and nobody had really envisioned at the time that it's going to be one of the major approaches to accelerating machine learning 40 years down the road, right? Okay, so weaknesses are also a place where you should think critically. In the end, every paper, every idea, everything we do has a weakness, right? There's no perfect thing in the world. There's a lot of imperfection. This doesn't mean that the paper, idea, or whatever is done is bad, right? This means that it's just, there are some things to improve potentially. So there's room for improvement, and future research can potentially accomplish this if it's worthwhile to accomplish. Okay, is that clear? Okay, and you will see some examples of this when you study some prior works. And then the discussion part comes in. For example, this is where you discuss potential ideas, and also hopefully you'll get to this through critical thinking. What are your thoughts and ideas? Can you do better? Can you solve the problem in a different way? Or should you be solving a different problem? Or can you maybe make the ideas better? Again, it's good to have an ordering over here from maybe the most important or most promising thing to the least promising thing, right? If you're tweaking parameters in the solution, that's probably not so interesting, right? The authors have proposed a solution. There's a lot of parameters. I'm going to tweak some of them. That doesn't sound very exciting. It's possible, yes, but it's not a big increment. Okay, and then takeaways, what you learned, enjoyed, disliked. And then we'll ask you to start the discussion. So as a presenter, you also have the responsibility to start the discussion. You can ask questions to the audience. I think this is where you actually can direct the audience to focus on some potential problems. And this is an exciting part, I think. You're essentially not just a presenter, but also a discussion leader, if you will. Okay. Well, I guess this doesn't apply to everything over here, but the summary. So we should really update this slide. So I'm going to give you a better breakdown of the time over here. Okay, this is one example of executive summary from one of Giray's talks. Giray is somewhere over there, or did he escape? Okay, he's there behind the light that I cannot see. Again, I'm not going to go through this in detail, but you can find that this is a nice summary that talks about the motivation and goal of the paper, and the problem that is studying, and the goal, and basically some detail about the experimental study to achieve that goal, and then some conclusions in the end, right? Based on the results, based on the experimental study, and then a final conclusion. So this is one way of doing the executive summary. Of course, this is done by a person who wrote the paper. You're going to be someone who is really presenting the paper, so you may actually add more. This is another executive summary from Minesh, another of my PhD students who graduated. Well, Guy also graduated, so he's not a PhD student anymore. But you can find a lot of these executive summaries over here. So this is the format that I suggest. Essentially, the summary itself of the paper should take probably less than 20 minutes. This includes the title, executive summary, and more detailed description. And then the analysis and the brainstorming should probably take 30 minutes or so. That brings us to 45, 50 minutes, let's say. Does that make sense? So try to stick to this. Sometimes the paper may be very complex. It may require 25 minutes. That's fine. But try to stick to these boundaries, right? As much as you can. Again, as I said, if the discussion takes longer than 30, that's even better. Right? That means that you inspired some people maybe with the presentation. Okay, so there's more advice on paper review and talk, both online as well as here. But this is a course where you would like critical thinking. to really thrive and become more and more. So be very critical. Not just be critical in the sense of nitpicking critical, but be very critical from a very broad perspective, right? Criticize as much as you can, question the problem also, right? Always think about better ways of solving the problem or related problems. Question the problem as well, right? Is the problem that the paper is trying to solve a valid problem? Or under what conditions is it valid? Is it a big problem? Is it experienced by a whole lot of systems? Or is it a niche type of problem? Will it become bigger in the future? These are all good questions to ask for critical thinking. And of course, reading background papers can help, both past papers as well as future papers, because you're going to be reading a paper that was written at some point in time, and there are past papers as well as future papers. And also, this is where some of your mentors can help. You can, of course, dig a lot, but your mentors who may be familiar with the subject a lot more can recommend that, oh, there are other papers on this topic. You may want to look at these resources. You don't have to read all of those papers, but you can quickly skim through some of them and say, in fact, some of those papers may actually have implemented some of the ideas that you may come up with while reading the paper. Okay, and this is really how things progress in science and engineering and everywhere, actually, by critical thinking, questioning, and improving things. Okay, we have a few sample text reviews provided online, but maybe more interesting ones are really the reviews that are, not reviews, but summaries and the discussions that are online on YouTube and past instances of the course. Okay, one thing I would recommend is to try to avoid rat hole discussions. You know about rat holes? They're not nice if you step into them. You may sprain your ankle or something. But it's the same thing basically over here. If the discussion becomes a rat hole, essentially you keep discussing something that's not that important, or something that's really common to a lot of things, and that's really not solvable by any reasonable means, unless you come up with a breakthrough in the rat hole, let's say, explode the rat hole or something, and then the rat hole doesn't exist anymore. Yeah, but basically these are some of these things. In fact, sometimes this happens, and I kind of break the discussion also, saying that let's get out of this rat hole, switch to a different topic, right? It's always good to do that. But basically, these four things especially lead to a lot of rat hole discussions. Workload. You can keep discussing the workload forever. Oh, this paper doesn't work for workload X. Good to state, move on. Yes, it doesn't. Maybe they didn't even care about workload X, right? Metrics. What is the best metric? Unless there's a flaw in the metric, probably not good to discuss for too long over here. It's better to discuss the ideas, right? Because that's where the real big progress happens in the end. Configuration, meaning experimental configuration, details. It's good to understand and acknowledge the problems over here, but it's not good to go into a rat hole over here, right? Unless you have a better methodology. Okay, these are pictures from one of my favorite books, actually. And you can see that the rat holes can be bigger, depending on, or deeper, depending on the situation. This is from this book, The Art of Computer Systems Performance Analysis. I guess it's too old of a book right now that nobody studies it. Do people study books these days? Not as much. You study books, hopefully, in the classes, right? Yeah. I don't know if there's an online version. Well, there may be one. Okay, but this book is one of the very good books on performance analysis in general, queuing theory, etc. And that's where I got this rat hole picture from, as you can see. And the focus here is on performance analysis. And I like what they say over here, basically. Even if performance analysis is done correctly and presented, it may not be enough to persuade your audience, the decision makers, to follow your recommendation. The list shown in the next box, not this box, is a compilation of reasons for rejection heard at various performance analysis presentations. These are actually good rejection reasons that reviewers use to reject papers also sometimes. Although they're much more creative than this, they come up with many, many different reasons these days. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new and that the analysis deserves more consideration. Also, the list is helpful in getting the competing proposals rejected. So he has a sense of humor also, as you can see. So basically, I think it's also good to look at the next part. There is no clear end of an analysis. Any analysis can be rejected simply on the grounds that the problem needs more analysis, right? That's true. There's no end. And this is the first reason listed in the box. And the second most common reason for rejection of an analysis and for endless debate is the workload. Since workloads are always based on the past measurements, their applicability to the current or future environment can always be questioned. It's good to know that also, right? Actually, workload is one of the 4 areas of discussion that lead a performance presentation into an endless debate. These rat holes and their relative size in terms of time consumed are shown in figure over here. So clearly workload is the biggest rat hole, as you can see. Presenting this cartoon at the beginning of a presentation helps to avoid these areas. So it's good to have a backup slide with this cartoon. If somebody starts questioning and getting into a rat hole, show this. And then maybe the discussion will change to a more productive discussion at that point. Okay, and this is the list. It's a bit focused on performance analysis, but basically you can see this needs more analysis. Reasons for not accepting the results of an analysis. This is also, I think, an example of closed-mindedness sometimes, in my opinion. But sometimes this is legitimate also, right? Sometimes the analysis is not enough. But the key is knowing when it is really legitimate and when it's not legitimate. I like this number 23. This impacts hardware. From a software person's perspective, that's a good reason. This impacts hardware. Let's not do it. Clearly, that has changed a lot over time. Another reason that's not very forward-looking, 24, that's beyond today's technology. That sounds pretty close-minded, right? Actually, we've gotten comments like this when we sent processing in memory papers. One of the comments was that gave a strong reject to a paper is DRAM manufacturers will never implement it. How can you rebut that sort of comment? Think about it. It's impossible that I can properly and scientifically address that sort of comment. It's basically the same as that's beyond today's technology. That's the purpose of research, depending on what you mean by technology, of course. And then I like the last one the most, I think. Why change? It's working okay. It's working okay, right? I mean, actually, all of our existing systems are working okay. Why should we complain? It's probably better than before, arguably in some instances, but the machine learning infrastructure is working okay at a lot of cost. It's okay. We can still live in this world. It hasn't exploded yet. Who cares about 50 years down? Let them deal with it. Okay, so hopefully you get my point. Okay, there's more advice on talks. There are many, like I will refer you to this presentation that gives tips for giving clear talks. And I agree with a lot of these things, actually. Every sentence matters when you give a talk. That's true when you write also. When you write, every single word and every single character matters. You need to guide the reader in the right way so that they really understand what you're talking about. They really get your points. Because the audience prefers not to think in general, right? About things that you can just tell them, right? And sometimes you want to guide them in a way so that you can really make them understand a complex concept without thinking, right? That's a very good presentation if audience learns a complex concept without thinking too much. Surprises are bad. It's better to say, this is actually a common issue that I see in papers also. People sometimes go into, this is how I do things, without motivating why I do things, right? This is the system I designed. Here's the implementation. Go deal with it. This has very little insight, right? It's much better to say, this is an overview of the system, and here's why we design each component. And then go into the details of the system, right? That's much better. That's a lot more insight. So insight is much more important. Explain every figure, graph, or equation. That's important. And when improving the talk, the audience is always right. Within limits, of course, right? But the audience gives you feedback, so it's good to try to address the feedback. Not all feedback is always good, but you need to take it seriously to understand whether or not it's a serious feedback, right? Okay. So I like also thinking about this thing. Well, there's a side channel here. Okay, I think I've already given the answer. Who knows about Salvador Dali? Hopefully more. Okay, who doesn't know about Salvador Dali? Don't be ashamed. That's fine. He's a very famous painter, Spanish painter, and he's not famous for this painting. What is he famous for? Can anybody guess? Yes.
The liquid drops.
Exactly, that's one of them, yeah. The passage of time, right, yeah. Well, this is another one. I don't know if I have the liquid, those clocks over here, but this is really the burning giraffe, as you can see. So it looks kind of crazy, but also very creative, right? He's really one of the surrealist painters that has provided a lot of momentum to that surrealism movement, and not just in painting, but also in art. And he did not start painting like this. This is one of his more crazy moments, I guess. He essentially practiced how to do things like this before he started breaking the rules. And I like this advice from K1. It's important to learn the basic principles first and apply them before you start getting creative about them. I mean, creativity is always encouraged, but it's always good to learn the basic principles on how to do things. And then once you actually master those principles, you can consciously choose to break them. It's good to think about this a little bit. I'm not suggesting this is the only way to do things, but when you're breaking some of the principles, it's good to know why you're breaking them and why you're doing things in a very unconventional way, right? I think we need to do things more unconventional ways, but if it's better if you really understand the downsides of the existing ways and actually attack them in a more informed manner. Okay, so how to participate? I think we're almost done, but I hope you come prepared. If you can read every paper, that's great. But again, that's not an expectation. If you can read the abstract, that helps. Thinking new ideas helps during the presentation also. If you didn't understand something during discussion, it's good to talk about this, read other papers. I think this applies for both the presenters as well as listeners, but reading other papers probably more for the presenters. Being critical is for everyone. Brainstorming and being open to new ideas is for everyone. Hopefully people will be paying attention, discussing, and contributing. And there's online before and after each meeting would be nice, but sometimes it's hard. Of course, I understand that. So let me go over the guided talk preparation in the last 10 minutes. So we will assign you a presentation date based on after we receive all of the orderings of the papers based on your preferences. And if you have a conflict, we need to know that as early as possible. Hopefully there's a good reason for the conflict. So start early, basically. Once you know your presentation date, it's best to start as early as possible. Study your paper and other papers that may be needed. And here, being careful, critical, and creative helps. We've discussed all of those. I mean, these are not requirements, but if you can actually try things on your own, that helps also. And please consult with mentors. Mentors are there to actually guide you through the presentation. And then you create a draft presentation similar to what we have discussed earlier. Hopefully you don't present all the details. That's not the goal, as we've discussed earlier. And then this draft presentation gets sent, you send it to the mentors, and you prepare for the meeting with the mentors. And don't schedule the meeting 1 week before your presentation. Schedule it as early as possible. What is worse than 1 week is 1 day before the presentation. And what is worse than 1 day is never scheduling the presentation. So clearly there are levels over here. It's a continuum. You should send the slides in advance, write down questions you may want answered, and make sure you address the feedback, take notes. And these meetings are really mandatory because it's really important for you to present this to someone else before it gets exposed to, I don't know how many people, a lot of people, right? We do this a lot in our research group also, right? For every single conference presentation, even though the conference presentation, even though the presenter may have presented and is an experienced presenter, we still go through a lot of dry runs because that way there are multiple benefits over here. You hone your presentation skills even more. You figure out what may be difficult to understand in the presentation and make it much more accessible. And you also figure out what questions may potentially come up and what you should prepare for in the live presentation setting. Right? So those dry runs are really useful. Okay, 2 meetings. Is that true? Okay. I mean, you could have more meetings, of course, assuming you're mentors, but you should address the feedback if you want to have more meetings. Okay, grading and feedback. So this is the grading rubric. I think this is also online. Is this true or? Yeah, I think the numbers, I don't know. So the quality of your presentation is the most of it. Basically, this is everything related to presentation. I think we can discuss more of these if you have questions, but we will take into account the difficulty of the paper. Not every paper is equally difficult. And also not some people will be presenting early in the semester. So those are the unlucky, not necessarily unlucky folks. Once you're done, then you don't need to present later, right? So there's a trade-off over there, depending on your comfort level when you present. But clearly, if those people who are presenting early will not have enough time to prepare, as much time to prepare, and we will take that into account. Synthesis paper is also a part of the grade, and it's already online. You can start studying. Attendance and quizzes is part of the grade. And then participation, we have a bonus grade over here, which enables us, if you participate a lot, for example, made the class lively, made the discussion good, then you'll get rewarded for it. But hopefully you're not doing this for the grades. In the end, this is only a 2-credit course, right? Yeah. Okay, so we will also try to give you feedback in class. Sometimes we run out of time, but if you want feedback from for your presentation, let us know if you would prefer to get feedback and prefer not to get feedback. Sometimes, we may not want public feedback. That's fine. But if you want to get feedback, please contact us. And if you don't want public feedback, please contact us. We usually don't get to it because there's a lot of discussion. So this may not be an issue, but definitely we may not get to giving you feedback, and please ask for it. Okay, this is the expected schedule. Again, we will meet once a week with 2 presentations per session. Well, there could be 3 depending on how many people remain in the course, because we don't have a lot of weeks available. Your presentations start on October 10th. This is assuming two presentations. I didn't do any calculation over here, but this may change. We may adjust it because October 10th is coming up soon, right? Okay. Yeah, and I think I've gone through the presentation length, etc. So a paper assignment will be done online. So study list of papers, and please check your email because this will be sent soon. The list of papers will be sent soon. And I don't know how many papers, but we usually assign we usually list 60 or 70 papers. In the past, we may have listed even more. And then you choose and rank some of your top choices. And please try to have a broad choice, because if you choose only one paper and say, this is the paper that I'm going to present, and if it's chosen by 10 other people, the probability that you will get to present that paper is going to be smaller, right? Because we can only assign one paper to one person. So try to choose more papers than, I would say, 5. Okay. Okay, I already said this. We need this homework to get started. And then there's this review. And then there's a paper review preferences. For that, you need to check your email. Okay. So how to approach this course? I think I've already given you a lot of this, but some of the comments that we received in past semesters from people is they learned a lot in this course. This is what people feel, I think. I hope that's true. I think that's true, actually. High investment, high return. That sounds like all my courses. And guidance from 2 top researchers in the field. That's actually good. I think they're referring to mentors over here, as you can see. Yeah. And also, I think there are some things that really, I like this one. I really love computer architecture. These are real comments from students. But basically, I think people have also said, it's not here, but the discussion, they really like the discussion when it's really interesting. And sometimes we give historical perspectives on the papers, and people find that very useful also. Because you read the paper and you may not have the broad perspective of what happened before and after. But giving that broad perspective is really important, I think, to place a work in a historical perspective. Okay, I think let me see, I've run out of time. Not yet. But hopefully you'll approach this as a learning experience. You'll do both critical thinking and decision-making, and also leading discussion. And hopefully this will enable you to do better trade-off analysis. Okay, I'm going to skip these because I already talked about a lot of these. But if you need to brush up on any material, you can find a lot of resources. You can, of course, ask us as well. Any questions? Yes?
Are the papers structured in like topics so that each week is a specific
Yeah, so we try to do that as much as we can, depending on the paper selections that people have, but we try to do that. For example, if there are 5 processing in memory papers, we will try to group processing in memory papers together as much as we can. But then there's schedule constraints, etc. There's also the mentor schedule constraints. So it's a complex scheduling problem, which is MP complete. So it's very hard to, I think, do that. Perfect scheduling. But we try. That's a good question. That way you can also see, and the discussion may be even better that way, right? But sometimes it's good to connect to the last week, for example. Oh, last week we discussed this, and today we're discussing this. If you're a presenter that's presenting later, you have the opportunity to do that. Yes?
Well, one question is more relevant to how you present. I mean, what you put in strengths and weaknesses. So, for instance, a paper was published maybe 20 years ago, and then in the aftermath of it, it has different strengths than what it portrays, or it has weaknesses that were evident. What you write, should it be as per what it was on that day, or should you also put in the context of what's happened after?
I would say both. I mean, you can say basically at the time the paper was written, the authors thought this way, but the real strength is this way, or real weakness that got discovered over time is this, for example, right? It's good to basically be clear. It's good to look at both that time and later. Yes, another question.
So we have to submit a preference to next week.
So we don't have a date for that yet. That's TBD, but you watch your email. We're going to send an email saying that this is the list of papers. Please submit your preferences. We'll send you instructions.
We have to submit something to next week, right?
So next week you have to submit what is this? Homework 0.
Okay, so
and then the week after you submit homework 1.
Okay, so the link, we will have to submit something about ourselves. Where do we find the link?
Oh, it's online.
Moodle?
Yeah.
Is it also on Moodle?
Yeah, exactly.
It's on the waiting list for the course.
Oh, okay.
Close next weekend. So until next weekend, I don't know whether I'm in this course for sure or not. So I don't have access to the Moodle until then. So
You can email us. Yeah.
okay.
I think the homework is online on the website, but you can email Mohammed,
Okay.
Lenny, and myself
Okay.
the homework. Yeah.
Okay, thank you.
Yeah. Okay. And hopefully if people are not going to take the course, they can drop it before the ad deadline so that people on the wait list don't suffer. Okay. That's all. Okay. I'll see you hopefully next week. Take care.